Bismillahirrahmanirrahim. Welcome to the another video session of the course M180. In this, I am going to discuss with you the topic called graphs. Now, in this topic, we are going to learn about the graphs, in which we will discuss the two types of graph, that is undirected graph and directed graph. Moving ahead, we are going to discuss graph traversal, two types of graphs traversals, that is depth first and breadth first travels techniques. Starting with a graph is nothing but a set of nodes linked by a set of edges, whereas a node is called a vertex, and the link between two vertices we call it as a edge. So, for example, this can be considered as V1, 1, 2, V2 or two edges, whereas two vertices, whereas the line which is connecting these two vertices is called as an edge. Undirected graph, in which the edges are not directed from vertex to another vertex. Okay, so in this one we can draw the vertices as circles. In graph in generally we can draw the vertices as circles and the edges as the lines connecting the vertices. Okay, so this can be an example of, or this is an example of a graph. Now here we call this as an undirected graph because the edge has no direction, whether it is going from a vertex V1 to V2 or it is from V2 to V1. Since there is no direction, no directed line from one node to another node or from one vertex to another vertex, such graph is called as an undirected graph. We can now, as I told, we can label the vertices V0, V1, V2, V3, V4, V5 and so on, and we can also label the edges as E0, E1, E2 and so on. Now here is a general definition or a formal definition for an undirected graph. It is a finite set of vertices along with a finite set of edges, whereas an empty graph is with 0 vertices and 0 edges. Now here in an undirected graph, each edge connects two vertices, and the order of the connection is unimportant because there is no direction from the direction of the edge from one vertex to another vertex. So let us say this as a graph. Now here let us say this is a graph G, whereas as we said, G is a set of vertices and the edges. Okay, so here we can write the vertices as a set of vertices. It is 1, 2, 3, 4, 5, 6. This is our V, whereas edges can be written as a set of E edge, that is 1, 2, then 1, 5, because there is an edge from 1 to 2, there is an edge from 1 to 5, then from 2 to 3 and 2 to 5 there is an edge 2, 3 and 2, 5, and moving ahead from 3 to 4 there is an edge 3, 4, then 4 to 5 there is an edge, and also there is an edge 4 to 6. So this is a set of edges, including the vertices plus edges gives us the graph G. Okay, because G is nothing but a set of vertices and the edges. Now here there are different types of undirected graph. There is a different types of graphs. This is called a connected graph, in which all the vertices are connected with other vertices. All the vertices are connected. There is no vertex in isolation, or no vertex does not have any connection with any other vertex. So such type of graph is called as a connected graph, whereas a complete graph, all the vertices are connected to every other vertices. So every vertex is connects to every other vertices. We call it as a complete graph. Disconnected graph, a graph in which we find some nodes which are not connected to the graph, connected to other vertices in the graph. We call that as a disconnected graph. Now coming to a directed graph, the formal definition for a directed graph is a finite set of vertices and a finite set of edges, whereas an empty graph has uh, empty empty edges and empty uh, vertices. But here the difference between the directed and the undirected graph here is the edge has a direction, the edge has a source and a destination, or edge connects the source to the target or to the destination. Okay, for an example, we see this graph is a directed graph, whereas the edge has a direction. For example, let's say it is v1 v2. So the edge is from v1 to v2. We cannot say the edge is from v2 to v1. Okay, whereas in, for example, if it is an undirected graph v1 v2, we can say an edge from v1 to v2 or v2 to v1. Okay, but here we cannot say that v2 to v1 in the directed graph. It is the direction is from v1 to v2. Okay, now it is a directed graph given over here. So again the graph, directed graph G, is what? It is a set of vertices and the edges, whereas the vertices over here are 2, 3, 5, 7, 8, 9, 10, 11. This is set of vertices, and set of edges are there is an edge from 2, there is no edge. There is an edge from 3 to 8 and 3 to 10, 3, 8, 3, 10, and then from 5 to 11, and then from 7 to 8 and 7 to 11, and then 8 to 9, and then from 9 there is no, from 10 there is no, from 11 to 2, 11 to 9, and 11 to 10. So these are the edges in direction. Okay, so hence this graph has the vertices, a set of vertices, and a directed set of edges. This is an example of using the directed graph in representing city map streets. Then there are some terms related to the graph that we have to study. A loop is nothing but the edge connects to vertex itself. We call it as a loop. For example, this is an let's say this is an vertex v1. Any edge is connecting to itself. Okay, we call it as a loop. This is a loop. Then path is nothing but it is a sequence of vertices from a vertex to another vertex, such that each adjacent paired vertices are connected by an edge. Okay, so for example, if this is a graph, so then we say the path from v1, v2, v3. The path from v1 to v3 is v1, v2 and v3. So v1, v2, v3. This is our path from v1 to v3. Okay. A cycle is nothing but any path which connecting the same vertex where it has started. Okay, or it is terminating at the same vertex where it has started. We call it as a cycle. For example, let us say this one, v1, v2, v3 and v1. That forms a cycle. The cycle over here is v1, v2, v3 and v1. So starting vertex and the ending vertex are same. That forms a cycle. Okay. Any connected graph T without cycle is called it as a tree graph, because since there is no cycle, then we call it as a tree graph. For example, over here, this is without a cycle. because you cannot form a cycle in this graph. This is called a tree graph. When a simple directed graph does not contain any cycle, we call it as an acyclic graph without cycles. Parallel edges, that one between two vertices there are more than one edge. For example, this is V1, this is V2. Okay, so if there are more than one edge, we call these two edges are in parallel, because it is going to starting from the same vertex and reaching the same vertex. I mean, starting from one vertex and reaching both the edges, starting from one and reaching the other. Simple graph has no loop and no multiple or parallel edges. We call that graph as a simple graph. Then a path is again the same thing, that is starting from a vertex to reaching the other vertices, going through reaching a destination vertex, going through the incident vertices. Now adjacency matrix, this is interrelates with the graph implementation. We can implement the graph in computers by using the matrix. We write a matrix of true and false, or 0 and 1, which is a Boolean value. So we write a square grid, that is a matrix of Boolean value that represent a graph. Now what is the size of this matrix is the number of vertices. The size of the matrix is the number of vertices. Now how to draw this matrix and how to represent this matrix when there is a given graph. For example, this is an undirected graph, and for this graph we have 5 vertices. So our size of our matrix will be 5. Okay, instead let me take an example for you. For example, let us say this is our graph. This is V1, V2, V3, V4 and V5. So 5 vertices, and it is a connected graph. Now here if you want to represent this in a form of matrix, okay, as I told, the size of the matrix is the number of the vertices. You have 5 vertices, the matrix will be 5 cross 5. That means 5 rows and 5 columns. The matrix will have 5 rows and 5 columns. So it is that this is vertex 1, 2, 3, 4 and 5. Over here vertex 1, 2, 3, 4 and 5. Okay. So here we write, if there is an edge from 1 to 1, that is a loop. If there is an edge from 1 to 1, we mark it as a true. Otherwise we mark it as false or 0. So if there is V1, 1 it is nothing but V1, V2, V3, V4, V5. Okay, and this is also same, V1, V2, V3, V4 and V5, vertex 1, vertex. If there is an edge from 1 to 1, we mark it as true, otherwise we mark it as false. There is no edge from 1 to 1, okay, so we mark it as false. There is an edge from 1 to 2, there is an edge, that is from 1 to 2, we mark it as true. Then 1 to 3 there is no edge, 1 to 4 there is no edge, 1 to 5 there is an edge, 1 to 5 we mark it as true. So whenever there is an edge from a vertex to another vertex, there we mark it as 1 or true, and whenever there is no edge from vertex to another vertex or to the same vertex, we mark that there as false or 0. Okay. Now let us take from vertex to vertex 2. With vertex 1 there is an edge, true, and vertex 2 to vertex 2, false. V2 to V3 there is an edge, true, V2 to V3, and V2 to V4 there is no edge, V2 to V5 there is no edge. The same V3 to V1 there is no edge, V3 V2 there is an edge from V3 to V2, so it is true. Then V3 to V3 there is no edge, false. V3 to V4 there is an edge, true, and V3 to V5 there is no edge. V4 to V1 there is no edge. V4 to V2 there is no edge. V4 to V3 there is an edge from V4 to V3, and V4 to V4 there is no edge. V4 to V5 there is an edge, so we mark it as through. Then V5 to V1 there is an edge, through. V5 to V2 there is no edge. V3 there is no edge. V5 to V4 there is an edge, and V5 to V5 there is no edge. So this is your adjacency matrix for the given graph. I hope it is clear for you that how to draw an adjacency matrix for the graph. In the same fashion, this is an adjacency matrix for this graph. Now coming to the adjacency matrix for a directed graph. In a directed graph, the difference is only that we take the vertex from 1 to 3, but we don't take the vertex from, we take an edge from 1 to 3 as it is in the direction of 1 to 3, but we not take it 3 to 1 because the direction is not from 3 to 1. So here the edge is considered from 1 to 3 only. We are not going to consider it from 3 to 1. So let us put this again over here in a directed graph. For example, this is V1, V2, V3, V4, V5. Okay. Now if it asks you to draw the adjacency matrix for this graph, then you write the size of the matrix, and it is its vertices V1, V2, V3, V4, V5. The same fashion V1, V2, V3, V4 and V5. There is an edge from V1 to V1, there is no edge, we mark it as false. V1 to V2, there is an edge from V1 to V2, we mark it as true. V1 to V3, there is no edge. V4, there is no edge. V1 to V5, there is an edge, we mark it as true. Then V2 to V1, there is no edge, because this edge is from V1 to V2, not from V2 to V1, so hence we mark it as false over here. And then V2 to V2 false, V2 to V3 true, then V4 false, and V5 false. Then V3 V1 false, it is false, it is false. V3 to V4 there is an edge, and V5 there is no edge. Then V4 to V1 there is no edge, V2 there is no edge, V3 there is no edge. Okay, V4 to V3 there is no edge, because this edge is from V3 to V4, not from V4 to V3. Then V4 to V4 it is false, V4 to V5 it is true. Then V5 to V1 false, because this edge is V1 from V1 to V5, not from V5 to V1. Then V2 false, these are all false. So this is an adjacency matrix for this directed graph. So this is how you can represent this. Now in programming we can represent any graph with the help of this adjacency matrix. The size of the matrix is the number of vertices or the number of nodes. Okay. We can also represent the graph by using a list called adjacency list, also called an edge list. Okay. Now what is the concept here is, for an edge list, first we are going to write all the vertices, and we see what are the edges going from these vertices. Okay, for example over here we first put the list of vertices, and we see from the vertices what are the edges going to where, to which vertex. So from 1 there are 2 vertices going from 2 going to 2 and 4, so we write from 1 there is a 2 and there is a 4. So from 2 there is 3 an edge going to 3, 4 and 5, so it is 3, 4 and 5. Then from 3 there is an edge to 4, from 4 there is no edge going out, so we leave it as null. And from 5 there is one edge going to 3, so we'll connect 3 over here. And from 6 there is two edges to 3 and through 5, so we write an edge to 3 to 5. This forms an adjacency list for the given graph. Okay. Now to put this graph in a programming, we consider it a simple directed and a labeled graph. We also give the label for the vertices. Okay, you can have the variables like boolean of edges and the object of label. For generalization, we make it object as the labels as the objects. We can initialize the graph variable, the graph, by using the graph constructor. The size n is again the number of nodes in the graph. We can add an edge. Adding an edge is from a source to a destination or source to a target. So when you supply the source vertex, for example v0 and v1, then there is we mark it as an edges of v0 to v1, 0 to 1, that is in the matrix. If it is 0, 0, 0, 1, for example 2, 3, 4, 0, 1, 2, 3, 4. So if it is an edge from 0 to 1, so 0 to 1, 0, 1 is marked it as true. Okay, so in this fashion, which is an edge is added. We can get the label for any vertex by using a label array. We can also check for an edge whether this is an edge or not, because the matrix stores true if there is an edge. So this method will return true if there is an edge, otherwise this method will return false. This is a method for neighbors, calculating the neighbors for every edge. Okay. Removing edge can also be done by making the array as false. For example, you want to remove an edge from v0 to v1, and this is your matrix. We have 0, 0, 1, 2, 3, for example 0, 1, 2, 3. So v0 to v1 there is a true, but if you want to remove this edge, you have to set that to false, meaning that this edge is removed. Setting the labels can be done by taking the object and assigning to a vertex. Size can be done. We can calculate the size of the graph, that is the number of nodes in the graph, by using the labels.length, because labels you are going to set for the vertices. Now looking at the worst case analysis for this, in the adjacency matrix, adding and removing of edges will take just a constant, whereas in edge list or adjacency list will take big of n, because you have to go through all the vertices. Checking of edge is present or not, the adjacency matrix take a small count, whereas an edge list or the adjacency list will take big of n. Iterating through vertices, both will take big of n. The edge list will take big of e, it is nothing but the number of edges, which is also depend on the number of vertices. This is all about how to about the two types of graphs, okay, and representation of the graph, that is directed and undirected graph, and its representation by using the matrix and by using the adjacency list. Now moving ahead to the second section of this unit or this topic, it has graph traversal. Graph traversal is nothing but moving to all the vertices, or traversing to all the vertices of the graph, okay, starting from a particular vertex. So it says start from a particular vertex and find all the vertices that can be reached from that from the start by following every possible path, that is by going through the set of edges. There are two techniques in this one, that is depth first search and breadth first search. So we are going to study these two techniques. In DFS we can use a stack or we can use a recursion to store a set of vertices to be visited. Okay, starting we consider the first vertex is visited and we are going to use a stack, okay, to fill these vertices in the stack, okay, and we are going to visit its neighbor until we reach the last node, okay, traversing through all the possible edges. Let us take an example first. Now let us take this graph, okay, with the vertices A, B, C, D, E, F, G, and we're trying to traverse this by using the DFS method, the depth first search method. We start at from the A, as we see, we take a stack to insert the values and we start from. Okay, so we are trying to start from A, so we insert A into the stack. Okay, and see what is the next neighbor of it. Okay, the next is to it is B. Okay, now the next to it there is also a G, but B is near to A, not G, or we can say that B is less than G. Okay, or before G. So we consider that value to be visited. So we insert B into the stack and we print B as visited. Then we have from B there is F and C, so we consider C, as the C is before F in the alphabetical order. So C is considered and we mark C as visited in the output. And then C has E and D. D is before E, so we reach D and we push the D into the stack and we mark D as visited. And then from D there is no more neighbors, or there is no more nodes. So at this point we are going to return back to C to see if there is any neighbor other than D. So to return back to C, we are going to pop out the D. Okay, so we pop out D, we are now at C. Now from C we are going to look whether there is any other. There is one more called E. So we insert E into the stack and we mark E as visited, that is as processed. And then from E there is a F, we mark as insert into the stack and mark it as visited. And then from F there is a G, we insert into the stack and mark it as visited. Then from G there is a A. A is already visited, so we are not going to take it, we are just going to pop G. So we are going to pop G. And then F. From F there is a B. Okay, B is already visited, pop F. And then from E, you go back to E. From E there is no more, we are going to pop E. And then from C there is no more to go, we are going to pop C. And then we have B. There is no more edges to go from B because there is an edge F, but F is already visited, so pop B. And then remaining A, pop A. So hence the stack is empty. At this point we are going to stop our program or our algorithm. So our output is the traversed vertices starting from A, that is A, B, C, D, E, F, G. Okay, this is the method for DFS. Now look at into the algorithm of it. Create a stack S, mark V as visited and push V onto the stack, that is A. We have started in our example A. And while S is not empty, pick the top of U, top of S, that is the vertex which is in the top of stack. Take it and you check if that vertex U has any unvisited neighbor W. If it has, then mark W and push it onto this stack. Okay, so that W will become the top. Then again you repeat the same. Okay, or else pop the S. I mean take out the last element from the S if there is no unvisited neighbor. Okay, this is the recursive method for this same DFS. Okay, I hope you got this DFS method. There is another program, another graph over here. Another graph for this traversing the directed graph by using the DFS. Okay, starting from a point vertex A. Now start from vertex A, the visited vertex A. What you traversed is A. Now the next it has B, E and D. B is nearest one or the lowest one, so we consider B. We push B onto the stack. So your stack has B and A, and what you visited is A and B. A and B, two you have visited. Then again from B there is E, so E you are going to push what you visit, A, B, E. From E there is H and F, but F is the nearest one. Okay, the or F is before H. So we consider F, and what you visited is A, B, E, F. Okay, from F there is a C, there is H. So we're going to go to C, and what we traversed is A, B, E, F, C. From C we have B. B is already visited. We are going to come back to F. Okay, by popping C. So here you are going to pop C. What you remaining is F, E, B, A. Now the top element is F. From F there is one more to be visited, that is H. Okay, so we are going to insert H into the stack, and what we visited is A, B, E, F, C, H. Then from H there is I. So insert I into the stack, and what you visited is A, B, E, F, C, H, I. From I there is F. F is already visited. Go back to H. There is no more nodes to visit, or no more vertex to visit H. From H then go back to E. From E you have visited F and H. Then go back to B, from where you have came. From B there is no more neighbors to go. Then from A again go back to A. Now from A you have visited B. There is D and E. So D is before E, so you visit D. No, you have came to here, visit D, and you mark D as visited. From D you have G, so insert G into the stack and mark G as visited. Now from G you have H. H is already visited. Go back to G. G has no more neighbors. Go back to D. D has no more neighbors. Go back to A. A has E is already visited. Then pop A. Finally, you are done with A, B, E, F, C, H, I, D. Please just wait for 10 minutes. I'll come. Okay, so this is again another graph for the traverser. It's a directed graph. So I hope you traverse this graph, and the result what you should get is this one. Okay, you have to start from the starting point A. Now coming to the second technique, or the second method, called breadth first search traversal. Now in this one we are going to use a queue instead of stack to store the set of vertices to be visited, and visit all neighbors before visiting any of their neighbors. So here the technique is that we are going to visit for any particular node all its neighbors before visiting their neighbors. For example, let us start from A. For this graph, insert A into the stack. Okay, the A is inserted into the stack, and check the neighbors of A. The neighbors of A is B and G. Now insert remove pop A and insert B and G. It is in the queue. You are going first insert B and then you insert G, the neighbors of the neighbors of A. Now B is at the rear end from where you want to delete. Now B has, you take out B, pop B and insert its neighbors. Neighbors are C and F. So insert C and F. First you insert C, then you insert F. Then you have B in the output. Okay, so you have B in the output and its neighbors are inserted. Then you have G. G has F and A. F and A. F is already in the queue. A is already visited. So you just pop G. Then C. C has D and E. So you pop C and add its neighbor D and E. Okay, and C will be as in the visited as the output. Now F has G and E and B, which is already in the queue and it is visited, and so pop F. Then D has no more neighbors, pop D. E has F and C, which is already processed, then pop E. Now your queue becomes empty. So at this point the traverser stop, and the output is this one: A, B, G, C, F, D, E. So this again, you can use this graph to traverse by using BFS. Now here the idea in BFS search is opposite to DFS. Now in DFS what we do is we visit a node. Okay, we start from a particular node, visits one of its neighbor, that is the nearest value, and then from it visit the another its nearest, and then visit its nearest till it reaches the end. Okay, and again come back to, if the end has no more, if the vertex has no more neighbors, then go back to its previous and check for other neighbors, and so on. Whereas in BFS we start from a vertex and we check all the neighbors of that vertex going to other neighbors before going to other neighbors. So we start from a particular vertex, visit all the neighbors, and then from those neighbors visit all of their neighbors, and so on. Now here the DFS uses stack or recursion and used in many applications, whereas BFS uses the queue and can be used to find the shortest path and also to find the shortest altering path for matching. Now here is an example. Given is the graph. What is the BFS for this graph? The breadth first search. Let us say we start from A. Now ask you to find the BFS. So what is the BFS for this one? First you have A, then its neighbors are B, C and E. So you insert into the queue. Let's say this is your queue. Okay, so you have A in the insert. A is popped out and its neighbor are B, C and D. B, C and E. Now pop B, neighbor of B is C, which is already over here. Then C, pop C, neighbor of C is E and D. So you pop C, add D. E is already there. Okay, then pop E. E has A and C, which is already processed, and then D. D has C and E, which is already processed. So your BFS for this graph is A, B, C, E, D. Let us take this graph as example 2 and answer the following question. What is the size of the graph? Size of the graph is nothing but the number of nodes in the graph. So, okay, so the size of this graph is 6, since it has 6 nodes or 6 vertices. What is the set of vertices here? It is A, B, C, D, E, F is the set of vertices. What is the set of edges? That is A, B, then B, C, then C, D, C, E, C, F, F, D and E, D. These are the set of vertices, edges. Then specify the path of length phi. The path of length phi, AB, BC, CE is 1, 2, 3, 4, 5. This is the path with the length phi. So A, B, C, F, D, E. So it is A, B, C, then F, D, E. Okay, this can be another path with length phi. Adjacency matrix. This is the adjacency matrix. As you know, we are going to mark F when there is an edge, when there is no edge from a vertex to that vertex. So from A to A there is no vertex, we mark it as F. And from A to B there is a vertex. From A to B there is an edge, we mark it as true. Okay, A to C there is no edge, we mark it as F. And A to D there is no edge, F. A to E no edge, F. And A to F no edge, F, and so on. Okay, so this is all what we have for you in this course as graphs. I hope you enjoyed this, and I wish you all the best for your exam. Thank you very much for watching the video.